So today we're going to be talking about 11.6. As you guys may have realized, there's about 2 more sections left in this chapter. Let's see here, 11.6, 11.7, 11.8. So yeah, our next exam will be over chapters 10 and 11. So I'm going to see if we're going to do that next week or the week after that. I have to talk with Dr. Zola about that. So we'll see when that's going to be. I don't see why it wouldn't be next week, but if he has something.
I mean, if it's next week, we won't have time to turn in this homework.
That's right. Okay. Yes, that works. That's fine with me. Okay. Yeah, I'm more than happy to give you guys more time to study, because that increases your chances of not only understanding it and doing well on it. So that's really good for me. That makes me happy. I'm completely fine with that. Plus, that gives me more time to grade, give feedback, and create the exam. So what we'll end up doing is we'll just start lecturing on the next round of material. And then while you guys are loading your test number 2 information in your brain. Okay, so let's talk about chapter 11.6, directional derivatives. So that's this thing called du of some f of xy. All right, so we'll realize that this is actually the same thing as dot ru. I haven't defined what that upside down Dorito and that f looks like, but it's called the Dell operator. The Dell operator on some function xy is defined to be partial f, partial x, partial f, partial y. It's a vector. So yeah, if you break down that bracket notation, that's what that equals in. If it's just an f, if it's just an x and y. If it's in x, y, and z, you get a plus partial f, partial y. You get a plus partial f, partial z, k hat. You get a k hat over there. Okay. So the book does a derivation of the directional derivative. So let's see here. I'll do a quick one. Basically, the concept behind the directional derivative is, remember when we had like a level surface? Okay. Actually, let's have one like the book had, because then it looks nicer when it's like that. It's like this projection here, like that. It has some surface like this. It has some curve on the surface. And we had its projection. So here's some point P, here's some point Q. P is equal to some X naught, Y naught, Z naught. Q is equal to some X, Y, Z. Okay. And so then you can project onto the XY plane 2 points. So we call this P star and Q star, for instance, where P star is the projection onto the XY plane, and Q star is the projection onto the XY plane. Really what we do is we set the Z component equal to 0. Then we notice that we can connect these two with a line, and that is the hypotenuse of a triangle. okay? Where we say, okay, this change is some HA, this change is some HB, or yeah, okay, and this is some H. All right. Basically, it comes from the concept of, let's say, we have some vector here, some generalized vector, and has some angle theta. Over here, it's x is your cosine of theta. If this is some h equaling this magnitude of your vector, it will be h cosine of theta, and this will be h sine of theta. Okay. So before, when we took partial derivatives, it talks about what is the rate of change purely in the x direction. And what partial derivative with respect to y is, what is the rate of change of the surface purely in the y direction. But the directional derivative allows you to understand or quantify a rate of change in any arbitrary direction, not necessarily just in the x or just in the y. Maybe like 45 degrees between them or 50 degrees between them, stuff like that. So now we're able to define any arbitrary derivative on the surface, okay? So let's create like a tangent plane here. Here's some tangent plane T. Okay, and some tangent line going through the point P. Okay. And we can say that this is some vector u. Then we can say PQ, P star Q star, same thing as HU, the displacement vector from P star Q star. Clearly, that's like x minus x naught, y minus y naught, 0, right? So what we end up getting is that's actually equal to HA, HB, because when you project them, that's these values. But this is also the difference between here. So final minus initial, right? So when you set x minus x naught equal to HA, and solve for x, you get this parameterization. Similarly, you would get this parameterization for y. This is a y naught. Okay. So then we define our directional derivative in the direction of this unit vector u as the limit as h approaches 0. I can delete this now. Of f of x naught plus h a, y naught plus hb, minus f of x naught, y naught, everything divided by h. So that's what that directional derivative limit definition is. Okay. So how do we, so one more theorem before we start to get to using it. Okay. If f is differentiable, so here's the theorem. If f of xy is this implies that the directional derivative in the unit vector u of f of x, possibly a level surface, is equal to this. Oh no, it's just your A. This is just your A. B. Where A and B are the components of U. Clearly, that's when in our previous formulation, H was equal to 1. So notice that this is like a dot product between U and the Dell operator, the Dorito. Okay, it defines the Dell operator here down the line here, or the gradient of F. So then let's define, so this right here is equal to the dot product between the gradient of F with this unit vector U. And now let me define formally again what the gradient vector of F was. You know, if you have some function f of x, y, then the gradient vector of that f of x, y is the vector formed when you take the partial derivative of it with respect to x and you put that in the first entry, and the partial derivative with respect to y and you put that in the second entry. That's why when you dot product this with this unit vector, you get this. Because this is the same thing as partial f, partial x. And this is the same thing as partial f, partial y. Right? Okay. So now let's actually apply it to a concrete problem. Making sense so far? This is a new idea. Mathematicians thought, why should we only be restricted to knowing how the surface changes in the x-axis or in the y-axis? What if I want to know if it changes in an arbitrary axis? This is how you do it. So what if I f of x, y is equal to let's find the directional derivative of this. Where u is a unit vector given by an angle theta is equal to pi over 6. And that it lies on the unit circle. Okay, well, recall from trigonometry, that's one of the special angles, right? At pi over 6, that's one of the special angles. Cosine is root 3 over 2, sine is 1/2. So in our picture, our unit vector is like this, and here's angle theta is equal to pi over 6. So its x projection has length this, and its y projection has length that. So now we want to know what is the derivative of this surface in this direction. And if you convert pi over 6 to degrees, it's in 30 degrees from 30 degrees above the x-axis. Okay. So now we know that our unit vector u is this. It is indeed a unit vector because look. Right? So 3 over 4 plus 1 over 4. Right? Okay, it's indeed a unit vector. So let's find the directional derivative remember, okay, so our A, so U is equal to AB. A is the square root of 3 over 2, and our B is 1 now. So notice that this thing is partial f, partial x, and now we got to compute partial derivative with respect to x. Okay, now we have to compute partial derivative with respect to y. Right? So, I don't remember, does this problem want us to evaluate at a specific value? No, it doesn't. It just wants to know what is it in general. So in general, we're just going to stick this here, put a root 3 over 2, and put a 1/2 there, and we're done. So, finally, this is equal to, okay. Then the problem says, okay, now that you found the directional derivative, what is the directional derivative's value at, some arbitrary point? I don't know, let's pick 0, 0. That's when I plug in 0 for x and 0 for y. Oh, well, that's kind of trivial. It ends up becoming all 0. Let's do something a little less trivial. Let's do like 1, 0. Okay. Okay, I just replace everything with the x with a 1 and everything with the y with a 0. Okay, so you get something like that. So you get 3 root 3 minus 3 everything over 2. That's just an example of evaluating it. Okay. All right. So now that we've done this, before I erase this function, actually let's just do a different problem. Because we need to do something unique. So we have some function. All right. What is the gradient of f? Well, this vector. All right. So to know what the gradient of f is, we need to compute the partial derivative with respect to x, which is 3x squared. And then partial derivative with respect to y is 3y squared. So the gradient of f now it really looks like a Dorito in orange. Sauce. Boom. So then, I've defined what the gradient is. Let's do another example. What if f of x, y is equal to x plus e to the x y? What is the gradient? Oh, calculate some partial derivative. Sine is cosine. Derivative e to the x is e to the x. Partial x of xy. Right? So then this becomes derivative of that is 0, so it's just derivative of e to the x, y, partial y. So I just get that's e to the x, y. So then the gradient of f is the vector formed by these two quantities. Oh. So then you can ask the question, what is the gradient of f at, let's say, pi and 0? This is what this becomes. Right? I'm trying to go above and beyond and put stuff that's not directly out of the book. So that function's out of the book, but I'm evaluating it at a different point. I'm starting to get a little bit more caught up in school, and I'm starting to have a little bit more time to invest in the quality of the lectures. Can't see the orange. Okay. Well, I'm gonna have to go back to the white chalk. Can you see the yellow? I'm running out of white chalk. Oh, you can see the yellow. Good. Okay. I need to go get some from my office, but I don't want to spend the time to do that. Okay. I'm just gonna make do. This is a hefty section. I'm glad this is not a quiz day. Hopefully we can get through all of it. Okay, let's say we have some function. Okay. So no, the directional derivative of a function requires a unit vector. It can't require any vector. It requires a unit vector. But we know how to make, given any vector, we know how to convert it to a unit vector. So first we got to convert this v into a unit vector. Okay. Then we can do this process. Recall that the directional derivative is the same thing as the dot product of the gradient with your unit vector. Meaning we need to find some partial derivatives. With respect to x, this becomes 2xy cubed. And with respect to y, this becomes 3y squared, x squared, minus 4. Okay. So then, when we dot product it with u, dot product it with u, we get 2 over okay. But we aspire to know what is it at 2, negative 1. So we replace all x's with 2 and all y's with negative 1. Becomes 4, becomes negative 4. This becomes 3, 6 minus 4 becomes a 2. Okay. So then I get negative 8 over square root of 29 and 10 over square root of 29.
This is the 2 squared, so it would be 12 minus 4.
2 squared, what's that?
Like it's in the parentheses 3 times negative 1.
Oh, yeah. Thank you so much. So that changes this piece right here, isn't it? This is going to change to 4 times 3, which is 12, minus a 4, which is 12 minus 4 is not a 7. 12 minus a 4 is 8. Okay, so that's 4 times 3. That's okay. Everything good so far?
Mm-hmm.
Thank you for that. So then this actually becomes 40. So it reduces to 32 square root of 29. Okay. Then your book goes on to define, I mean, this goes without saying, but I might as well just write it down. That's how easily it generalizes. So what if I give you a f of x, y, z? What is the directional derivative? Let's say at 0.130. In the direction of a vector v, let's see what 1, 2, -1. Okay, so still the directional derivative is still equal to this. So first things first, we need to convert our vector v into a unit vector. Okay. So we get there. Okay, so then we got to take partials. Okay, so this is sine of derivative sine is cosine. Partial y of yz is just z. Partial z. I get this is derivative sine is cosine. Partial z, that is y. Okay. So the directional derivative is del dot u. So becomes our x 1 times RU. So I'm going to factor out a square root of 6 out of the whole thing. So this term will have a 1 times something. This term will have a 2 times something. This term will have a -1 times something. This will be our sine of YZ. This will be our XZ cosine of YZ. And this is going to be our XY cosine of YZ. Okay. And we want to know what is it at 1, 3, 0. So we just replace our variables in our expression with that. So this all becomes 0. Z is 0. One times 3 times cosine of 0 becomes a 1. Okay. So then this reduces to 1 over square root of 6 sine of 0 is 0. That is 0. This becomes a 3 times a -1, which is just a -3. So this becomes -3 over square root of 6. We can rationalize the denominator to get this, which reduces to, right? Reduces to, oh, correct? But notice that it's the same thing as this. Is it not? Yeah, that's why your textbook ends up getting this as a value. It ends up expressing this like so. It was perfectly accurate to express it like this, and it was perfectly accurate to express it like that. You know, on a test, I won't care if you express it like that or down here, or if you express it like this. Typically, we like to rationalize the denominator, but it's not the end of the world if you don't, if you ask me. But computer stuff will probably have an issue with you doing that. So, but thankfully, this is not an online inputting course, so you guys don't have to worry about that. Okay. So now let's talk about how do we get the maximum value of a directional derivative. Well, it's actually really easy. Think about what the directional derivative is defined as. It's the dot product here. But remember, the definition of dot product means that this is true. Right? But recall that the magnitude of a unit vector is just 1. So we get this is true. And recall, this expression has highest value when cosine has highest value. And cosine has highest value, I say to equal, 0, which is like pi. I mean, which is 0, which gives me cosine of 0, which is 1. Just put a 1 there. Okay, so then we get that the directional derivative has maximum value, the absolute value of the gradient, or the magnitude of the gradient, which, remember, this would then equal so what does this mean? Well, it means the directional derivative will have a maximum value if it is running in the same direction as your gradient is. So here's a cool example. If you're given okay, and you start from point P is equal to 2, 0, 2, which is equal to 1/2 2. What is the u of f of x line from P to Q? So this means that PQ is our vector of V. To get that, we get final minus initial. Final minus initial. And we get final minus initial. So this becomes 1 minus 4 all over 2. Over 2. So this becomes negative 3 over 2. Okay. That's our V. We have to turn it into a unit vector now. So So that becomes root 25 over root 4, which becomes 5 over 4. So then this becomes 4 over 5 times your original V, right? Negative 3 over 2, 2.
Would it be 5 halves?
5 halves. Yes, you're right. You got to take the square root of the 4, yeah. Thank you so much, Jamie. Thank you so much. So then this becomes, and then this becomes, this is our unit vector U now. All right. So we want to know the directional derivative. Okay. So we want to know this value. Partial x to that is just e to the y. partial y of that is just right? It ignores the x, it differentiates e to the y, that's just e to the y, partial y, which is just 1. So this is what you get here. Then if it asks you to evaluate at some point, just plug in values for x and y. Then, if it asks you for the maximum rate of change, okay, maximum rate of change, you know that by that calculation we did earlier, the maximum rate of change is just the absolute value of the gradient. So let's say at 1, 2, what's the max rate of change of the directional derivative? Well, that's equal to this. Recall would equal just your, so for instance, I'm just picking 1, 2. So then this which becomes e squared root 2, for example. Okay, well, I didn't get to as much as I wanted to. We didn't even talk about the tangent planes and whatnot. This was a pretty hefty section, so we're gonna have to talk a little bit more about it next class period.